An implication expresses a relationship between two statements. So our statements might be P and Q, and so an implication would be of the form P implies Q, or if P, then Q. And it's often useful to study related implications formed from the same statements P and Q. So given an implication, if P then Q, then we can define a few related implications, and we name those. So the converse of if P then Q is if Q then P. The contrapositive is if not Q then not P. And the inverse is if not P then not Q. So an example, if our implication is if it is raining outside, then it is cloudy, then the converse would say if it is cloudy, then it is raining outside. The contrapositive would say if it is not cloudy, then it is not raining outside. And the inverse would say if it is not raining outside, then it is not cloudy. One thing I want us to look at, and we'll discuss this further in a little bit, but just with this example is let's assume this original implication is true. So if it is raining outside, then it is cloudy. I know that it isn't, always true. There is such a thing as sort of like sun showers, I guess, but the rain is coming from clouds. So we'll just assume, okay, if it is raining, then it is cloudy is true. Let's think about these other statements. So is it true that, let's look at the converse, is it true that if it is cloudy, then it is raining? I don't think that's always true, right? There are certainly cloudy days where it is not actually raining. So that one would be false. What about the contrapositive? If it is not cloudy, then it is not raining outside. So if we're going to assume that the original implication is true, then if it's raining, then it is cloudy. So if it's not cloudy, then we could assume it is not raining. So this one would be true. What about the inverse? If it is not raining outside, then it is not cloudy. Again, sort of like the converse, I don't think this one's always true. There are certainly situations where it might be cloudy but not be raining. So notice that the original implication and the contrapositive have the same truth values, and the converse and the inverse have the same truth value. So that's something we're going to be exploring a little bit further here. And so that's coming up right here. So relationships between these statements. The converse and contrapositive both reverse the direction of the implication. The contrapositive and the inverse both negate the hypothesis and conclusion. The inverse is the contrapositive of the converse, and the converse is the contrapositive of the inverse. Quantified statements. So when working with quantified implications, so namely implications that include the for all or the, there exist, we ignore the quantifiers when forming related statements. So for example, we might have a statement for all x, if p of x, then q of x. The converse is for all x, if q of x, then p of x. So we don't do anything with that for all x when we sort of describe the converse. It just comes along for the ride. Same thing, contrapositive for all x, if not q of x, then not p of x, and the inverse for all x, if not p of x, then not q of x. A note on existential quantifiers. So statements of the form, there exists an x such that if p of x, then q of x are unusual because they're automatically true whenever there exists an x for which p of x is false. So, because the false, if the hypothesis is false, the entire statement is true. For an existential quantified uh, implication to be true, all we need is for one x to make that whole statement true if that p of x is false for that x. So again, sort of an unusual type of a statement to see. However, the same rules would apply for converse, contrapositive, and inverse. Equivalent statements is something we were talking about earlier. So an implication and its contrapositive always have the same truth value. An implication is not generally logically equivalent to its converse. However, if both P implies Q and Q implies P are true, then we write, this biconditional. And we would sometimes write if and only if, right? So P if and only if Q. So an example, we could say an integer n is even if and only if n squared is even. This means that we sort of have two statements that we're looking at. If n is even, then n squared is even, and then if n squared is even, then n is even. So in terms of when we're talking about more terminology, we often when we're talking about statements would talk about this idea of necessary and sufficient conditions. So if we say Q is necessary for P, that means that if P then Q. So P implies Q. If we say P is sufficient for Q, that means that if P then Q. So if P is necessary and sufficient for Q, then we could have the biconditional P if and only if Q. So an example here, we could say being divisible by 4 is sufficient for an integer to be even, and being even is necessary for an integer to be divisible by 4. Or we might have a statement for a square matrix having non-zero determinant is necessary and sufficient for invertibility. Why does this matter for proofs? Thinking about necessity and sufficiency can help guide proofs. So if you want to prove a statement, you might ask what conditions would be sufficient to prove this. If you assume a hypothesis is true, you might ask what facts must necessarily follow.